So here we're going to review some information from 1211 on polarity. So I want to start with, we're going to go over these molecules I have listed here, N2 through CH2Cl2. First, I'd like you to look at this and pause me and try to identify which of these are polar and which of these is not. So I'm going to go over the answers, and then we're going to talk about each of them. So for the ones that are polar, you're going to get that this one, CH3Cl and CH2Cl2, these two are polar. The other four are not. If you are very comfortable with why these are polar and why these are not, I'm not as concerned about you watching through this. But if you weren't able to easily identify which of these molecules are polar or not, this review video is for you. Especially, and you can fast forward a bit if you can watch sort of the screen as do it, if you only had trouble identifying this one as polar, if everything else felt okay, that one at the end sometimes gives people issues, which is why I'm going to end the video with it. So let's start with N2. So if we look at this molecule, we have a nitrogen attached to a nitrogen. And if we do its Lewis structure, we have 2, 4, 6, 8, 10 electrons. So we end up needing to get a triple bond here. So we move some of these over here into the bond, and you end up with nitrogen triple bonded to nitrogen. Now in this case, you have two of the same atom. That means their polarities are exactly the same, which means this is nonpolar. So if you have two identical atoms, or let's say you had multiple identical atoms, it's all the same atom, and they end up being equally the same electronegativities, that means there's no polar bonds at all. So you can't have a polar molecule without at least one polar bond. So that gets through that one. Now, let's look at CH4. Again, this is a case where it's important to note that the CH bond, without having to worry about the whole Lewis structure, is considered a nonpolar bond. Even though these are two different atoms, their electronegativities are so close on that scale that we used in 1211, it means that they had a difference of less than 0.5. So because they're so close, they end up being nonpolar as well. We don't see a significant amount of charge difference on one atom versus the other when we're looking at a carbon-hydrogen bond. And CH4 has 4 carbon-hydrogen bonds. We get the tetrahedral molecule that looks like this. And so since there are 4 nonpolar bonds, we end up with a nonpolar molecule because, again, we can't have a polarity issue, a polar molecule without at least one polar bond. Now, third, let's look at a molecule that does have some polar bonds but ends up being overall nonpolar. So if we go through all your Lewis structure rules, you'll end up with 2 double bonds to oxygen by each carbon in CO2. And initially, you might think this was polar because there are indeed polar bonds. The carbon is more electropositive than the oxygen, which is more electronegative. So you have 2 arrows pointing like this. Remember that CO2 is a linear molecule, like we learned from our VSEPR structures in 1211. It's got 2 electron groups. So the oxygens are exactly opposite each other. Since they're exactly opposite, it functions like a tug of war. Since it's the same atom on each side, both oxygens pull, but they're pulling equal amounts. So even though any one CO bond, double bond, is indeed polar, they both cancel each other out. So we end up with an overall non-polar molecule. Now, this same idea is going to happen with CCl4, but it can be a little bit harder to see. So with CCl4, the carbon-chlorine bond is indeed polar individually, but when we get 4 of these, they end up canceling each other out. Now, just looking at this picture, I can understand if you had trouble knowing, hey, how do I know these cancel each other out? So let's look at the actual molecule itself. Let me switch over. No, not that one. Webcam. I just moved a whole bunch of stuff in my options around. So this is the CCl4 molecule. I'm going to try. So what's happening is this carbon in the middle. You'll notice there's 1 chlorine on top, and there's 3 of these chlorines at the bottom. Now what's important about that is if you look at the distance here, this is much taller than the distance down here. Specifically, if you measure it, this is going to be 3 times as tall as above the carbon compared to these 3 chlorines down here, which are going to be much less distance. So what that means is that, remember, this is the z-axis. So this is the up and down axis. It means that the up of this chlorine up here is going to cancel the down pulls of these 3 down here because these 3 aren't as far down. So it's like 3 tiny down arrows balancing out this one big up arrow. So that'll cancel the z-axis. Then you're left with 3 atoms in the xy dimensions that are able to pull at each other, and it works a lot like a trigonal plane. Well, not like, it's exactly like a trigonal planar molecule. Where what happens is, let's consider something like BF3. So this is what a trigonal planar molecule would look like. So you have one up arrow and two going this way. And so these arrows get broken up into a left and a down and a right and a down. This is like breaking apart the components of a vector in math. So what happens is the left and the right cancel each other out. But the down component of those adds together to make a larger down arrow. But that larger down arrow is exactly the same size as the larger up arrow up here. So their electronegativities are able to cancel each other out. It's like thinking about a tug of war where you have three people of equal strength on each side, and they try to pull that center point. It's going to exactly cancel each other out. And that's because they're all spaced away as far as possible. So in that case, the three chlorines that are around the bottom here are going to be able to cancel each other out in the XY direction as well. And we're not going to work with polarities much for molecules bigger than tetrahedral. So I'll go ahead and mention that if you end up with tetrahedral molecules and you have 4 of the same atom, then it's going to end up being nonpolar because whatever polarity difference it is, they're going to be able to cancel each other out. Now, if they weren't the same atom, that isn't true. So let's look at CH3Cl. So I'm going to make that molecule real quick. So we said that CH4 was nonpolar and CCl4 was nonpolar, but let's look at something like this. So now you have this big chlorine on top, and there's nothing to balance it out because these hydrogens and carbons are nonpolar bonds. So we're going to have a lot of electronegativity up top and then not much at the bottom. Note that you can rotate this molecule and you can still see that it's not distributed evenly, right? Like, so if I did it this way, we have a big pull over here. So it's not just, oh, this top version, because this is symmetrical. We can rotate it around and we'll always have that one chlorine that's a bit off. Now, the one that's sometimes harder to see on paper, we're going to look at first in a picture. So if you look at this here where you've got 2 chlorines, what you'll notice is both chlorines have to be on the same side like this. So like if I rotate it around, like I can change it, right? Like I can exchange these, and whatever I put them, you're always going to have them so there's one side that's close together. And so those sides are going to be negative, and then that makes this side more positive. So even though there's 2, and I think on paper, we'll just look at paper just a second, it looks like, oh, they cancel each other out. But when you actually make something with your model kit, no matter where I put it, I can keep exchanging them and I can keep rotating them. I'm always going to end up with 2 being close to each other, which gives us one side that is different than the other side. Now, what does that look like on paper? So the issue on paper is, we'll just go to another screen, is that you have, let's say, CH, Cl, ClH. So when you draw the Lewis structure, you might draw it like this. And on paper, then it looks like, oh, the 2 chlorines are opposite each other. They cancel each other out. But they're not really opposite. That's why we worry about what the shapes look like. So if we instead draw it as a hydrogen with a carbon, and even doing it this way, right? Let's say this is our drawing. The problem here is that over time, I think you'll get a feel, that's 3 Cls. That's supposed to be an H. So we just do this little modification. It's an H. So over time, especially if you stick with chemistry and you end up in organic chemistry classes, you'll start to get a better feel for these shapes. But at least for me right now, when I was in general chemistry, I didn't yet have a good feel. Yeah, I could draw these wedges, and I was like, sure, that's sticking out of the paper, and the chlorine is in the same plane as the paper. But like actually looking at a model helps a lot with this. So like that molecule, I have 1 chlorine. Let's go back. There we go. So what I have is I have 1 chlorine that's supposed to be perpendicular to the carbon, and then I have 1 pointing away, because that's the wedge. We also could have done one like this, where we have it like pointing away towards B. You can't see it very well, but it's that way. And then 1 that's even. So those are hard to see. I'll also use this as a recommendation that when you get to organic chemistry, getting one of these little model kits can be worth it. I have definitely found it really useful as a student when I was working on things. They come with a bunch of atoms and you can make molecules, and it helps with working through the shape stuff. Because one thing that'll be helpful is once you've practiced them some, the same shapes keep coming up. So if I take this and I say CH2Br2 instead, you just have to replace these with some other atom. Honestly, we can just imagine the green is bromine instead. I don't remember what color we used to represent bromine in our model kits, but the idea is it's the same way. It's a halogen, so it can only be connected to one place. Looks like this. So as we do this more and more times, you get to where you're like, oh, this molecule looks not like another molecule I've seen before. So if you can get to where you're comfortable with the idea that this is polar, but this is nonpolar, the CCl4 variant, if you can get through those two, I think you're in a pretty good spot for polarity. Also, if this wasn't enough, feel free to use your textbook, as well as I'm pretty sure I have a 1211 video if you go to my YouTube channel on polarity, and look at other sources too. This is a topic where I think seeing other people say it differently makes a big difference. Because as much as I'm going to try to help you with this particular figure and talk about it, I know that getting that geometrical field can be hard, so feel free to use other sources as well. And obviously, if you're in my class right now, I'm happy to answer questions as well to try to help you see why some of these are polar and some of them aren't. So with that, I hope this helps out and that you get through this part of 1212 okay, because I know it's hard when you have to go back to the 1211 stuff.